We started this chapter by studying a simple spring mass system with K and M, where the only force acting on the spring was the restoring force, or acting on the mass was the restoring force of the spring, minus Kx. From this we found the angular frequency of the system to be K over M. This is the frequency that the system will oscillate with if it's left to its own means. It is also called omega 0, or the natural frequency of the system. In the second step, we did not only have the mass from the force from the spring. Let's put our equilibrium position here. But we also had some damping force, taking energy away from the system, minus b times velocity. In this chapter 40.8, we will add one more force. And this is an external force. It could be, for example, pushing the mass in some manner. And we'll make it sinusoidal as well. So it's some force amplitude F0 times sinusoidal form omega t. So it's been applied at frequency omega, which means that the direction of the force will change as a function of time. So that's why we have the double-sided arrow here. If we solve the ensuing equation of motion, we'll get the following result. The displacement as a function of time will be some amplitude in the sine of omega t plus the phase angle phi, where the amplitude A0 is a bit more complicated than it was before, because it involves the new force term here. So the amplitude of the force F0 divided by m times square root of the angular frequency of the external force minus natural frequency of the system. They're both squared, and that the whole thing is squared. And then we have some term from the damping. Let's forget the damping for a while. So without damping, the amplitude A0 is F0 divided by m. And because this is 0, we're only left with the omega terms. And in fact, the second power will cancel out. Now, if the omega is really close to the omega 0, the natural frequency, we see that the amplitude becomes very large. And if they're exactly the same, the amplitude goes to infinity. And this is without damping, of course. The condition where the angular frequency of the forcing function is very close, or even the same, as the natural frequency of the system is called resonance. In resonance, the amplitude and energy of the system increases rapidly, possibly all the way to the extent that the structural limits of the system are exceeded. And then we can have bridges collapsing and glass breaking. In real life, we always have some damping, so we go back to this formulation. And in this graph, we have plotted the amplitude in 3 different cases of damping. So in the first one, the curve A, we have some damping, but it's reasonable. And you can see that as the frequency of the forcing function omega is really close or exactly the natural frequency of the system, we have this sharp increase in the amplitude of the motion. If we increase the damping, we get the curve B, where the resonance is still visible, but it's definitely deflated. And also notice how the resonant frequency shifts to the left. And this was because in the previous chapter we learned that the natural frequency when there's damping is not k over m, but it has the additional term from the damping b2 divided by 4m squared. So whenever we have damping, it will reduce our natural frequency, and we see this shift to the left. In curve C, the damping is so large that the resonance isn't visible anymore. Therefore, it's possible to get rid of unwanted natural frequencies and resonances by introducing enough damping. And this is practiced widely in engineering, for example, in constructing buildings. In this chapter 14.8, we didn't have any examples to be solved, so that would be all for chapter 14.